G'day everybody, we've got Monica Anderson here, and she's an expert in artificial intelligence. Has been working on AI for quite some time, especially on artificial general intelligence. So without further ado, I'll put a link to the bio in the description. So let's get right to it. So Monica, welcome. It's great to have you here.
Thank you. I'm happy to be here.
Mm-hmm. So look, let's ask firstly, how did you first get into artificial intelligence?
Well, it started in college. I was getting a few classes of AI, and I was in fact a teaching assistant on the AI group for the freshmen, on AI classes for the freshmen. And we ran a few lab sessions taking apart various things that counted as AI at the time. And since then, I've been working in industrial grade AI, if you want to call it that, for many, many years, and until 2001, when I kind of split my attention between doing AI for others the way they usually did it and doing some research on my own into what I perceived was going to be the next way to do AI, which was deep neural networks. And so it's a pretty unusual career path, if you will, switching that early, because most people only got into AI around 2012 when deep learning got to be very popular. And I basically had like 12 years of head start on getting into the deep neural networks. Now, remember, I was doing my own kind of networks, so they were very different from deep learning, not very different, just the right amount different from deep learning. So that's what I've been doing. That's basically my main focus of my research is my own kind of deep neural networks, which are called organic learning, and we can talk a lot more about those.
Right, yeah, so that sounds really interesting. So historically, at first, I think people really wanted to solve the big problems in AI, and then found it was too difficult, I guess, because of computing power and all that sort of thing. So how do you see the history of AI and how it shaped AI development and it for better or for worse? Yeah.
Oh, sure. So AI officially started in 1955 with the Dartmouth conference, and there was a handful of people who started the conference, and Martin Minsky and John McCarthy were the biggest names among them. Solomonov was there, but the one forgotten name or rarely talked about name is Oliver Selfridge. And Oliver Selfridge was the only person on the conference that basically insisted or wanted to work on understanding of things, how to get from low-level representation to high-level representations. And in the end, he was overruled by Minsky in the final paper, where Minsky basically said that we'd like to work on understanding, but we don't know how to do it, so we'll just focus on behaviors. And that set the course for AI for the next decades, where people basically copied behavior in computers by directly programming the behavior into the computer. And that's not really AI, because all of the understanding of what's going on is in the programmer's head, and all we're doing is we're basically making the computer behave the way that the programmer wants it to behave. And Selfridge went on to publish a number of papers about things like what he called the pandemonium system, where he had a system of demons, and the demons were shouting to each other. So the lowest level demons were basically looking at the world, if you will, and they were shouting upward what they saw in some descriptive terms, and the demons at the next level would listen to those, and they would shout upwards what they heard from below. And after multiple layers of demons, you basically get the top level, you got the highest level understanding of what was going on at the bottom. And this is like extremely much like deep neural networks work, like including deep learning. So this was kind of proposed 1958, 1959 after the conference in Selfridge's papers, and of course he was ignored because everybody else was doing this. Let's program some learning into this. Let's program some behaviors into the system. And that was basically what AI was all the way up to 2012. There's many, many different branches of AI at the point, if you will, all the way up to that point. And they all solved different sub-problems of what they perceived as the main problem, but nobody really looked at the most fundamental issues of AI. And there were many reasons for that. In some sense, what Minsky did was right. I mean, it's the machines at the time, they could not handle anything except simple models of the world which were programmer generated. That's the only thing we could fit in our machines. So that was the correct thing to do in some sense. We couldn't do any better. But around 2006, the machines had gotten a lot better. What happened was that a professor at the University of Toronto by the name of Jeff Hinton and his team of students over many generations of students were basically working on neural networks all the way from something like 1984 or something like that. And Hinton had already written several chapters in the book, which is known as the Connectionist Bible, which is it's called PDP? No, yeah. It's the book about that defined neural networks and connectionism. It was published in 1982, and it was written by Rumelhart and McClelland, with Hinton was the major unnamed author at the beginning. So all of that, basically, what happened was that Hinton's work finally started working, if you will, at 2006. And the reason for that was manifold. He had 4 algorithm improvements to whatever counted as neural networks back in the 80s and 90s. And he had large amounts of training data with the internet, and he also had very large computers. And he had started to use matrix algebra and to do the computation of the neural network. And that was very efficient for the kind of problems that he was working on. He was working on recognizing things like handwritten digits on check books and other things. And that worked out. Like I said, that started working in 2006, and they continued working on those strategies and those algorithms. And by 2012, they won several competitions, and now everybody understood that this was the way forward for this very critical understanding part of basically how do you go from sensory input such as pixels to an understanding that this is the digit 4, or the understanding that's a cat and that's my favorite chair. So how do you go from low level to high level? Suddenly that problem had a solution in the vision space. And that was a first, and it was not just a tiny improvement over what had gone before. They basically broke all the records with tens of % of margin, which was unheard of. I mean, in signal processing was one of 6 disciplines where the new methods really worked well, and they were looking at 20% improvement overnight in a field where you had, say, 1% improvement in a decade. And similarly for vision understanding and certain aspects of language understanding, etc. So this was a very big deal in 2012. And there was a stampede of researchers to switch to this new deep neural network, to deep learning strategies. But many of the old school people who had worked with the model building over the years, they didn't want to switch. They thought that it was antithetical to everything they had been working on. And some resist to this day any notion of using neural networks as a path towards artificial intelligence, especially general intelligence. And so that's a split in the community that remains to this day. Most of the people who are working on deep learning today, they are basically fresh out of school in the past decade, since 2012, I should say, 6 years, and they are very good at what they're doing, and they're really using these tools well. And so I think of current AI mostly being deep learning.
That's interesting. So we're going to be focusing on whether deep learning has understanding. But first, before this interview, for those who didn't read the title, it'll be focusing on artificial understanding. So, but before we get too deeply into the mechanics of it, let's talk about definitions then. And it's important to understand what you mean by understanding.
Yes.
It may differ from some people's versions or definitions from understanding.
Correct, yes. In my writings, I use understanding with an uppercase U at the beginning and reasoning with uppercase R. to basically say these are my definitions of the terms. But the key insight goes back many, many decades, all the way to Darwin, if you will, who discussed it early on. But many people over the years have basically discussed this split in attention, or this split in how the brain works. And Daniel Kahneman's book, Thinking Fast and Slow, is the most obvious or most explicit about these things. And he basically splits the human mind into subconscious understanding, which is intuition-based, and conscious reasoning, which is logic-based. And so those are very different. And it's there are very many things. If you split the process of intelligence, if you split intelligence into these two parts, if you will, and they do interact and intermingle in interesting ways. But for pedagogical reasons, if you look at how they're different, there are many, many things that follow the same split into the reasoning and understanding part. For instance, reasoning is reductionist, which means that it uses models of the world that you are manipulating mathematically, like formulas, etc. You use high-level understanding of things, high-level enough to be called models, and you use those models to reason about things stepwise, one after the other. Whereas understanding is this big, just basically looking around the room, understanding what's going on, or reading a sentence or hearing a sentence and understanding what it means. This is the low-level processing that happens before we become conscious of what's going on. I mean, you don't know how and why you understand this sentence, okay? It's completely hidden from you. It's completely in your subconscious. Kahneman has an interesting example in his book, which is basically, he says that one of the things that differs between these two modes is that understanding is basically reasoning can be stopped and continued. You can plan a European vacation, and it might take you several days to figure out all the train stops and hotels to stay at. But you can basically sleep in between each of these segments of reasoning about your vacation. Whereas understanding, once you, for instance, learn to understand your native language, it cannot be turned off. So you see there's a very big difference in how they work. And there's I have lists of differences between the reasoning and understanding part, between the etc. That affect basically everything. Starting from including the fact that the whole understanding part is unscientific, it is non-scientific, it does not use science, it doesn't require complete information, it doesn't follow logic. All it is basically a best effort guesses what's going on, and it does that guess really well based on a lifetime of experience. And so understanding is the ability to jump to conclusions on scant evidence, and that's 99.99+% of what the brain does. And our reasoning is a paint-thin layer on top of the understanding of the world that we have. And that's the only part we're conscious of. So that's a radically different view of intelligence than what most people have. To most people, intelligence stops at the reasoning level because that's the only thing they can see using introspection. And that's what I call the introspection trap. Just because you can't see the subconscious, which I said is 100,000 times larger than the conscious part of the brain, if you count activation cycles. Understanding is much, much more important than reasoning for intelligence.
It's interesting because a lot of people see understanding as having a clear, conscious knowledge of how a model works, but you've got a different sort of take on that. Yeah,
it's not really different. I mean, you have an understanding of how a model works. Take like F equals ma. If in order to use that to, for instance, measure the horsepower, estimate the horsepowers of your car, you basically you weigh the car and then you floor it to see how fast it accelerates, and you measure that and you figure out the acceleration. Now you can guess how many horsepower you have. The reason you can do that is that you understand what F, M, and A are, what they mean, what it means in this specific case. It means the mass of your car. It doesn't mean the serial number or anything like that, the VIN number. It's basically you yourself understand enough about physics and about the equation to be able to use it in real life by applying the right pieces from the world into the equation. And that understanding is something that's much harder to express than just a simple F equals MA formula. It is a lot of information that goes into that.
Interesting. So you've heard of Mary's room experiment. It may not directly apply, but let's just say, do you know this one, the knowledge argument in philosophy?
No, I don't.
Okay, well, just imagine you're a lady called Mary who spends her whole life in a grayscale room.
Yes.
And becomes an expert neuroscientist on the knowledge of how color works. So you know all there is to know about color, and then you walk outside because the door suddenly opens, and then you suddenly experience color. Do you think she understands color before she walks outside?
I have no clue. That's a deeply philosophical question, and it's one of those things. I mean, there are very many interesting questions that you can waste your entire life on, and I have basically a little box of red herrings that I call them, which includes things like this very puzzle, and things like the Searle's Chinese room and the Turing test and all kinds of garbage that I don't. Qualia is the first thing in the box. That I basically don't feel like dealing with. It's a distraction. I have, by my studying epistemology, I have basically a very simple-minded view of what understanding is, how you can implement it in a computer, and I'm going ahead and doing that. And I don't particularly need to understand what qualia is, because I can get the system from knowing nothing to understanding something useful, and that something useful may be monetized, etc. Why should I bother whether there's any qualia involved or not, etc., etc. So I don't know if Mary, the black and white / color person, has any understanding of color beforehand. It is very close to the argument about reductionism versus holism. So it's not irrelevant in this context. It's just that I don't like the puzzle as such. I'd like to find more obvious things that we can discuss that aren't puzzles, such as
like learning to ride a bike, right?
Yes,
so
that's a good idea.
And at first, I don't understand it. I know that I'm meant to circle my feet around the pedals and make sure that I'm moving my arms to steer the front wheel in the direction I want to go. But it's not until I guess, learn the muscle memory and internalize the process.
That is exactly.
Do I understand it once I've internalized and it's become more like a bodily function? Is that what you'd say?
It's too much to say bodily function even. I mean, it's everything we learn is like that. Some of the stuff we learn from listening to others. Some of the stuff we learn, but physical skills are more obviously subconscious, if you will. And my example of that is, for instance, it's known that what you see, before it gets understood by the brain and becomes part of your conscious, there is a delay of half a second, 500 milliseconds roughly. That's called a Libet delay, which means you are actually living half a second in the past. Okay? Now, if you're living half a second in the past, you couldn't play tennis. And if you're a beginner at tennis, you can't play tennis, because you go down to the tennis court and you see the ball coming against you, you're trying to compute where it's going to be so you can hit it, and you're going to miss because it was there half a second earlier. And you have to basically play enough tennis and constantly correct small mistakes that you make, so that your subconscious, I mean, if this is your subconscious and there's a layer of consciousness on top here, if this is your subconscious, initially you start at the bottom and you go all the way to the top and down again, and that's too slow. But as time goes on and you learn more about tennis, you basically make little loops here that says, okay, I can see a ball on my right and it's there, and I tell my arm to hit it right there. And your conscious self is not involved. I mean, you have to play tennis subconsciously. Inner tennis, I think it was called 20 years ago, 30 years ago. You have to play tennis subconsciously. You have to ski and ride a bike, etc. These things are basically almost completely handled by your subconscious through these shorter paths that don't take half a second to traverse. And those only appear after a lot of practice. Yeah.
Mm-hmm. So let's talk about like the difference then between reduction and holism, which is something you write a lot of about in your essays. Does that sound like a logical next step at this point?
We can do that, yes. Reductionism and holism are basically two terms that go back at least to the 1920s. They come from epistemology, but already the Greeks were debating this thing. They just didn't use those words. So I have, if you will, I looked at the definitions for reductionism, and there's a number of them in Stanford Encyclopedia of Philosophy. And if you look at all of those definitions, they all have one thing in common, which is that they deal with models. And so I boldly went ahead and said, whenever I say the word reductionism, I mean the use of models. And models are things like scientific models, naive models that we make ourselves but don't tell anybody or don't publish, etc. They are mathematical hypotheses, they're formulas, equations, and computer programs. They're basically things that we use to describe reality in simple terms. And in describing reality in simple terms, we have basically discarded about a lot of complexity in the process that's also called reduction. I mean, reductionism is the use of models, and reduction is the process that allows you to use models. You start with an unreduced reality, which is everything you know, everything you see, everything you hear. And from that, you basically extract a little equation that you're going to either invent it or you're going to use it. F equals ma is an example of a model of that kind. So reductionism is the use of models. And once you have said that, you can switch around and say, what is holism? Holism is the avoidance of models. So if you look at both of them have basically problem-solving strategies. Reductionist problem-solving strategies is to take the problem apart into pieces, and you take each piece apart into smaller pieces until you have pieces that are so small that you can solve them. And if you can solve all of the small pieces, you can solve the big problem. That's the theory of reductionism. This works a lot of the time, but it requires an understander. It requires somebody who understands the big picture and can do this thing. You have to have a brain, basically. You have to have an intelligence of some kind that does the reduction from the big, rich world to the simple model that you can speak about. Now, humans do reduction all the time. We see something, it basically hits our eye, and we can talk about pixels in the eye if we're not particularly, well, we want to talk about rods and cones and stuff. The pixels are then processed in the vision chain, and the vision chain then at the end says that we have, this is for instance a cat, or this is my favorite chair in the living room, or this is a car, or whatever you have. And the reduction from pixels to the cat is basically the key problem in intelligence. And most people have ignored that problem. Like I said, our AI up till 2012 was mostly ignoring that problem. So the holistic problem-solving view is that you don't go from the problem to a model space, which is mathematically pure, where you can do computations on the model and solve the model, and then you can apply the results back to reality. That's not how we do it if you do the holistic problem solving. In the holistic problem solving, we solve the problem in the domain where it appears without ever going to models. Let me give you an example of that. If I'm giving a talk and I look at the wall and it says maximum occupancy at 200 people, and I look at the audience and I say, okay, there's no empty chairs in the room, so we have 200 people here, roughly. How many of them are women? Well, in the US, roughly half the population is women, so we can say there's 100 women in the room. That's using reductions. That's using models for everything. I have one model that says how many people can be in this room, and we look at the seats and we say they're all occupied, and we say there's 50% women. Those are all models. And so the answer 100 women is an approximation. It is how we would do it if you were scientific about it. We would use models for everything.
Yeah, if we didn't have time to count everybody, yeah.
What do you say?
If we didn't have time to count everybody, like
counting is
millions of people in
counting the women is the holistic solution. you don't use models, you just count them. That's the holistic way of doing things. And most of the time, the holistic solution tends to be more expensive than the model use. And that's why we use models. That's why we use science and math, because it gives us shortcuts to many, many problems. As long as we can understand the problem and know what models to apply, it gives us a lot of leverage at solving problems cheaply. But most problems can also be solved holistically. Now, there's the strangest thing about this is that the majority of problems that any human being solves on any given day are holistic. We are not using science for anything. You can make breakfast without reasoning or using science. You can drive your car without using reasoning or using science. When you come up to a stoplight, you don't compute the differential equation to determine how hard to push the brake. You just do it. You're solving it with the car as being part of basically of your environment, and you're affecting it, and you're directly using feedback to do it. You're not involving any models of car travel at all. And when you're making breakfast, you just do whatever worked yesterday. The holistic answer to almost every problem is, if it worked last time, do it again.
So you've spoken about abstraction, and that's something that scientists use a lot. And, in pure model space, it's what scientists would use to refer to all sorts of things. So, but that relates to reduction, isn't it?
Absolutely. Yes. In fact, reduction is a synonym, if you will, to abstraction. And the reason I'm using a different word is because abstraction comes with a prior meaning, which is used in mathematics and by others in physics, etc. And abstraction in that sense is magic. It's just expecting to exist. I mean, some of you, we abstract this to that. Okay, fine. Nobody asked how you did it. Whereas if you're doing AI, you have to know how to do it. You have to actually have an answer for that magic part. And so the answer to that is the abstraction is done using reduction. And I'll describe reduction in some detail in a moment. But basically, we call it reduction just to remind ourselves that the kind of abstractions we do, we can't just declare them to be magic. We have to actually know what we're doing. And reduction is a recipe for how to do this abstraction, if you will. And the recipe is a little bit surprising, which is that if you have, for instance, all these pixels and you're trying to figure out is there a cat in the picture or whatever, you can't, the key point is, can you figure out what matters? What's important in the picture? What's noise? What's irrelevant? What is important? What do we have to pay attention to? What is worth learning? And what can we ignore? Even
what's salient?
Yeah, what is salient? That is exactly the term we use. And so it's a tricky question. And the surprising answer is that it is easier to figure out what is not salient. It's easier to figure out what's irrelevant. And what you do is you throw away that which is irrelevant. And if you do that enough, you're left with that which is salient. So that's a very handy trick. And that's exactly the trick that we use in deep neural networks. When you get it, let's take the deep learning example. You get basically a picture of a cat in the form of pixels or something like that. And you recognize things that are basically, okay, so here is a big gray area, and that looks irrelevant because I've seen those before. And you throw away what you can. And then you say, okay, here's something looks like a little gray line, and the next level up says it's a cat's whisker, and the next level up says there's a cat's face, and so on. You can discover these things by throwing away everything else at each layer. And the trick about reduction in multiple layers is that you don't know what's relevant and what's irrelevant until you understand stuff at a certain level. So you can understand some stuff at the pixel level, but not much. But if you find sub-patterns, you can understand the sub-patterns higher up, and so on and so on. And so you, at every layer, as soon as you discover that this part of the image is irrelevant, or this middle representation is irrelevant, you throw that away. And what's left is basically this trumpet, if you will, of stuff that starts wide and ends up saying it's a cat at the very top. And that's roughly how deep learning works. My AI epistemology primer at artificial-understanding.com discusses this in 5 chapters in quite some details. Basically shows that all neural networks, all deep neural networks have this ability to do discarding of the irrelevant in multiple steps and ending up with that which matters.
Mm-hmm. That's interesting. So, I mean, the reductionist similarity here is like, the divide and conquer approach in software development, and the falsification approach within our philosophy of science cover. So, I mean, it's a similar strategy there.
Similar, I don't know if it's similar. There are similarities, but we are in this process. We are basically using guessing a lot. I mean, we are not scientific about it. We have very arbitrary ways of deciding what matters and what doesn't. At least they look arbitrary to somebody with a scientific background. And there are no guarantees. I mean, understanding is, like I said, is jumping to conclusions on scant evidence, and it is not repeatable. It is not, doesn't give you all the answer. It doesn't give you the best answer. You have no guarantees of any of those things. Doesn't even guarantee you can terminate. So we have, it's a very different strategy, and this is one of the big problems in trying to get people to switch to neural networks in general, or to switch to organic learning, is that we have to give up. We have to take our scientific education that we have and put it in a box and close the lid. Because none of the things that we talked about, like you said, falsification, etc., hypotheses, those things, yeah, they kind of are hypotheses in the system, but they are made by the machine. They're not made by us. So you have to basically, what you're doing when you're working on neural networks is that you're creating a framework that can learn. And this framework then learns, and whatever it learns, it's basically in the corpus and whatever, and it's decided by your algorithm what it keeps and what it throws away. But there's no guarantees. One corollary of that is that all AIs are fallible. All intelligences are fallible. There is no perfect intelligence. Basically, the dream of a super intelligence that never makes a mistake is the reductionist pipe dream, and it's never going to happen. Can I do a little demo here?
Yeah. I was thinking it was a good time to do that. Yeah.
Let's start it. Let me do a little bit of screen share here, and I'll tell you what's going on.
Fantastic.
So
it's great to actually cover that reductionism and holism too.
Yeah, it is very, very important. You can't really go into AI without knowing what's going on. So here I hope you can see a green screen. So
I can see you like still, but I can see the green screen behind you.
Hang on. Let me push one more button here. There we go. How about this?
I do. I see the green screen.
All right. So here's just a regular Unix shell, and I have a program which happens to be called UM2, which I like to run. And it's basically my artificial understanding, if you will. It's running the organic learning algorithm is trying to read a book. In fact, it's trying to read multiple books. It reads a book in a few minutes.
LCHARS, what does that stand for?
It's the learning characters. It's how many characters it has learned, how many characters it read from the book so far. So it's read, 16,000 characters right now from the books. There'll be more things to show on that line in 500,000 characters, because the 500,000 is we run tests. We run tests every half a megabyte of characters. So a megabyte is roughly a book, a little bit more than a book. So we read 3/4 of a book and we run a test, and we read another half a megabyte and we run another test. It's the same test. The system, we can use the same test every time because the system doesn't remember the test. We turn off the learning by setting one boolean to false, and then it cannot understand, that cannot learn from the test case. So we can use the same test over and over. So we let it read half a megabyte, we test it, then we test it again every half a megabyte. We'll get back to that in a moment.
Yeah, so we've got another few minutes before that.
Yeah, it's going to take a few minutes before it gets there. So let's stop the share and go back to the camera.
So let's talk about fault tolerance just briefly then. I think that's useful. In terms of like, we have models that don't gracefully degrade at the edges of their applicability. and more of a holistic approach might be able to make educated guesses, or sort of guesstimates the edge there, which might, I'm not sure if educated guesses was the right word, but learned guesses, which might be more accurate.
Those are good terms. What there is basically, there's two kinds of mistake, and computers rarely make a mistake, okay? But when they make a mistake, it is like you said, at the edges of their competence of the model that they are basically running. And those mistakes that they make, they are expensive, spectacular, hard to immediately correct, and hard to remedy, and they don't learn from them. But when a human makes a mistake, like suppose you're learning to walk and you kind of got the hang of it, but it gives thresholds and stairs and other things gives you problems. And so you basically, every time you make a little mistake, this mistake is small and easily correctable and immediately remediable, and it's not spectacular. It's like looks like you stumble a little bit. And you learn from every mistake you make. And that's one of the key distinctions in my mind about whether something is a general intelligence or not. It's a general intelligence if it can learn from its mistakes.
Mm-hmm.
If it can't, it's not general. Mm-hmm. Another important distinction is whether you use models or not. If you're making models of the world, or if you make a model of a small part of the world, you're limiting your computer to only working on that small piece of the domain, a small piece of the world. Whereas if you start out with an empty machine that doesn't know anything, then it can be general. I mean, the model is not general. The model is whatever you program, that's all it can do. But if you start with a machine that's empty and it learns everything as it goes, then it can potentially learn anything. And all general intelligence are learning machines.
You mean like a blank slate? But humans,
yeah, it's a blank. I start with a blank slate. My machines are empty when they start. You saw here, we started with 0 characters. It knew nothing about English or Chinese or Japanese when it started, but if you give it English books, it will learn English. If you give Japanese books, it will learn Japanese. So it's a completely blank slate when it starts, and it learns whatever you give it. So it's an artificial general understanding. What do you say?
Would you say that's a requirement for a general intelligence? Because
it is absolutely, yes. A requirement for general intelligence that it is a blank slate.
Well, humans aren't blank slates, but therefore I imagine that you say that humans aren't general intelligence.
Well, they are. No, the newborn child is pretty much a blank slate.
Okay.
I mean, there's details. We can argue about the details. We can argue about physiology, whatever, developmental stuff. Outside of the scope of this discussion, in theory, the theoretical intelligences are all blank slates in the beginning, and they have to learn everything, because if they don't have the capability to learn everything, they can never be general.
Mm-hmm. Mm-hmm. Okay. So if they do start with models, the models that they start with will hinder generality in the future. Is that what you mean? Exactly.
Yes. All models of the world are detrimental. And it is really, I mean, people argue that you should start with models because they give you a bootstrap so that you can get going faster. And they are deluded, because if you're trying to measure what the intelligence your system is learning, the stuff that you put in at the beginning, the reductionist model-based stuff, is going to overwhelm all the measurements you're trying to do. So you can't actually tell if your learning algorithm is doing anything, or if you're learning, or if all the results come from your models. And it's really hard to tease those apart. So you're doing yourself a disservice by starting from models. And also it is very hard to build a system that both learns and has models and can basically merge the information from both. I have not seen a way to do that.
Well, I guess people are trying. I think Kristen Sorensen is doing something like that, and Ben Goertzel is trying to achieve that with OpenCloud.
Yes.
They haven't achieved it yet. So you think they're doomed to fail?
I think they're doing the wrong things. And in general, for the layperson, if you want to estimate the chance of an AI project's success, you count the number of boxes in their block diagram, and if they have more than 3, they're likely not going to make it. I mean, if your idea about intelligence is to have an intelligent machine, an AI, an AGI, is to have 30 boxes which have labels like language understanding unit and prediction unit and reasoning unit, you don't know how to implement a single one of those generally. You can do the high-level reductionist breakdown of what we perceive intelligence to be, but it is not the reality. It is a lot of stuff has to be like interacting, interwoven into one single unit. And that's in the brain is basically neurons and synapses signaling to each other. That's all there is, a single black box with neurons and synapses in it. And if that doesn't do 99% of what you want, you probably have a poor outcome, or then you haven't understood the problem.
So, like, interesting progress in neuroscience is discovering more and more about how the connectome works and how all these neural patterns work. Would you predict that once we get finer-grained abilities to take 3D videos in real time of what the brain's going on, we'll be able to use those algorithms to improve upon the deep neural networks?
I'm willing to bet money that that will be too late. We will already have AI by the time that's possible. Mainly because basically I'm on a faster track than neurosciences. I'm starting with epistemology. I figure out how we can learn it all, what intelligence is, how reduction works, how can you implement reduction in a machine. If you have those as your primitives, you can do a lot of progress, and you don't have to actually look at neuroscience much. I look at it every now and then for purposes of tie-breaking, whatever, or implementation hints. But basically, epistemology gives you way more implementation hints than neuroscience does at this point. And so I think I'm way ahead of a lot of other people who are building neuron-based systems that are closer to what they perceive the brain to be. An example is spiking neurons, which the brain basically uses. I have figured out that the spiking neurons is there to solve a very complicated problem that I'm not going to get into, but I have solved it in a different way. And so I don't have to do spiking. I basically have single 0-1 impulse signaling from neuron to neuron through a synapse. And that works just fine. And so the neuroscience will lead you astray. You can find, based on epistemology, you can find shorter, faster answers.
Sure. I mean, evolution got to where it was, not by completely redesigning.
My soundbite for that is that the story about what what the brain has to do is much shorter than the story about what the brain does.
Okay. Sure. Yeah. I wonder if your test is complete.
Let's go take a look at my experiment. Yes. Share screen. So what we see here is that it has actually...
I can't see the screen.
Oh, I'm sorry. There's always this button called share screen that I forget to press. Okay, here we are. You have basically, it says here that after the test UC, which is an unsupervised congruence test, has run for after 434 seconds, it had read 500,000 characters. 342 seconds were spent learning. The rest was spent testing. And it ran 0.37 tests per second, and it got 19 things wrong. The error rate is 19%. Now, what is the problem we're trying to solve here? Let's take a look at that. So here are basically, this is what the test that is running. I'm giving it 2 sentences, which are labeled like P1 and P2. You can see them highlighted in blue here, and they're the same sentence, except in the blue highlighted part. In the first, it says, the captain was sick and prudence forced me to consider possibilities. And the other one, it says, the captain was and prudence sick forced me to consider possibilities. They're basically, we've taken the first sentence, duplicated it, and then we have mangled it a bit to make it look like ugly English. So I call this the ugly English test. And then the computer basically reads both of those, and it has to decide which one is uglier. And here it says that the correct one is number 1. Well, it just ran through 100 of these sentences, roughly at this complexity, and it got 81 of them correct after having read 1 book. So if I gave you a book in Turkish that you've never seen before, or some other language you've never seen before, could you, after reading 1 book, start figuring out what's good and bad Turkish? I mean, I actually have a slide for that. Let me see if I can find the slide.
It'd be interesting to try.
Right.
But I wouldn't be knowing what I was reading. I mean, if I read a book in Turkish.
Right.
I've been to Turkey, by the way, last year, so I probably know a little bit.
There is a bit of a there is uncertainty about the there's uncertainty about the validity of the test, or how deep you can you really call it understanding. So these are all good questions, but I soldier on and basically say it's good enough for me. Take a look at this. Here's basically one sentence, and then we have moved the word around, and you can easily tell which one of those is correct, right? Which one is the best English. That's easy for you to tell. Well, try again. So this is Finnish, and you have no clue which sentence is correct Finnish and which one is ugly Finnish. So the only difference between the top two sentences and the bottom two sentences is that in one case you know language and the other you don't. So that's why we believe this is a good test for language understanding. This is used in the industry. It's published in 2012 by Noah Smith. So it's other people are using it too. And there's a number of other tests that I'm also looking at. I've done several of them. But for our everyday work, the ugly English test you're seeing here is basically what we rely on from day to day to tell whether we're doing better or worse. And I should possibly, we may not have time to look at all of this, but the spoiler is basically that this thing will go down to 3% in a matter of hours. 50 minutes or so, it will get to 5%. And we will see.
We can keep it running in the background and have a...
Yeah, we keep it running. It's gonna, if you wait another 20,000 characters, start running tests again, and it's not very spectacular, but it's different.
Yeah, you see that it'll have a better level of accuracy. Right?
So 2, 1, go. Here it starts switching to the test, and it runs test case 0, 1, 2, 3, etc. And when it gets to 100, it prints another line, and it's going to say record 11 or something like that. So that's how that works. And basically we've been running these tests. I mean, this test is, I've been running this test for maybe 6 years, 7 years. And we've done many other tests. Amazon review sentiment is one we've done. We looked at the what's called the closed problem with a Z. We're now looking at the GLOO set of problems, which are basically the second generation, if you will. I mean, most of the tests that happen, most of the existing tests that are used in the industry are too simple for us, and we can't really handle those because they are made for the old kind of NLP kind of systems that got by with different surface understanding, and we want to basically read the whole paragraph to get really into the problem statement.
And that was a question I wanted to bring up too. Like, if we can just do a quick interlude, there's something called natural language understanding and image understanding.
Right.
So what do they mean by understanding, and how is it different from your?
Well, let's look at image understanding briefly. I mean, if I share a screen again. So let's look at this: 95, 96, 97, 98, 99, 100, 11%. And it reads 1,200 characters per second, 1,300 characters per second still. It doesn't actually go down that much. And that's a good sign, because if you read a lot of books, you don't read slower. And our system basically is constant speed. It drops a little bit, but in theory, it's constant speed. And when you get, after you read 100 books, the 101st is going to go at the same speed. Anyways, what I wanted to show was this. So this is already from 2012 or 13. There's an image that you can give to a computer, and it comes back with these bounding boxes, identifying things in the image, and says, woman in white dress standing with tennis racket, 2 people in green behind her. You really can't fault that for being incorrect. It's quite amazing. And this was impossible until 2012. This was only possible to do with deep learning. We had no clue how to approach the problem before then. And this is reduction from an image to internal concepts that can then be associated with colors and things like tennis racket and woman and dress and all of these things. And it's all learned by the computer.
And that's a sentence if you put all those words together. Woman in a white dress standing with tennis racket.
Correct. It being a sentence may be more luck than design, but basically, yeah, that's roughly what it is. Oops, I don't have a mouse here.
So is that version of understanding closer to what you see as understanding?
I would say that version of understanding is basically understanding for vision, for images. That's state-of-the-art image understanding. And the fact that you can go to an internal representation and then to text that is correct, that is, in my mind, that is a very good sign that there is some kind of understanding going on. But we don't know our own understanding how it works because it's subconscious. So who are we to say that we are any better? It's a lot of jumping to conclusions. You see a cat's whisker, you guess that there's a cat. That's the kind of stuff we do all the time, and that's the kind of stuff we are basically raising our computers, teaching our computers how to do.
Interestingly, the Deep Dreams software which came out, what was going on there? What was going on behind the scenes? The use of deep learning and what it had already understood as like being salient in images before were being sort of woven into sort of an artistic rendition.
Yes, yes. Deep Dream was very fascinating, and it's one of the bigger wonders of Deep Dream that most people don't notice is that if you look carefully at the Deep Dream generated image, there are no cut and paste lines in there. It didn't do it by cut and paste. It did it by synthesizing every pixel in a context. So it's not just pasting dog snouts on everything. It basically thinks that this is a good place to have a dog snout, and then it creates one from scratch. Yeah, it's. I think of Deep Dream as basically as a looking glass into the vision, understanding, intelligence, and looking at intermediate hypotheses that it has discarded. So they are unlikely to survive all the way to the top. If you go, there's a depth parameter in Deep Dream, and you go to the top. I mean, it says dog or something like that, and the dog snouts are there on everything in the middle. That's not. I mean, I don't use Deep Dream myself. I'm a bit on thin ice here, but that's basically how I think of it. We have similar effects in the text area. We're basically trying to generate text. And we're trying to generate language from deep structures. So we have our system read a paragraph of text. And then we look at the intermediate structures in short-term memory to figure out what did it understand from this paragraph, what did it think was the most important terms at the top level. And then we say, can you make me a sentence from what you know in the brain, but use half as many words? And that would be a summarizer, which would be a real product. So that's one thing we're working on. And so we look at different levels in the system, and we have different kinds of textual representation in the middle, and it doesn't all make sense, just like Deep Dream doesn't make sense.
It's interesting from an artistic point of view to look at, but it's not finding all the salient aspects and representing them in a sort of an accurate way. It's more like a cool sort of image at the end. Yeah. Well, what about natural language understanding? Like, do you think what's going on there is relevant to the term understanding that you're using? I expect so, yeah. Yeah,
first I have to clear up.
Language.
Yeah, I have to first clear up the little confusion that some people use natural language understanding as meaning voice understanding. And that is unfortunate, but that's not something I'm going to try to correct. I'm just going to mention it. I use understanding basically as a differentiator to natural language processing. NLP is using reductionist models of language such as grammars and word lists and synonym lists and stemming and all of this garbage to try to understand language piecemeal by models. They make models of everything, parts of speech, etc. And just knowing that something is the subject of a sentence doesn't really help you understand it, does it? And natural language understanding, NLU, in my book, is basically the trying to go directly to something that is an understanding very similar to the way we have in the brain, where everything is built out of patterns of text and overlapping sentence fragments and overlapping intermediate concepts. And then at the top level, you have basically winnowed it down to the one true concept for what this paragraph is about or whatever. And so that's a different view, if you will, of how to treat language, and it is like radically different. It's as different from NLP as deep learning is from early vision experiments.
Okay. Well, back to the sort of the fault tolerance aspect, and the world. You brought up in your writing, I think, the frame problem, where the world changes while we build models, and so if we have a model that that we build given a certain context in a given time, that context will likely and often does change. Even language drifts over time. So
yes, the world changes behind your back. That's a short formulation of the frame problem, which was written by John McCarthy and Pat Hayes back in the 60s. In some sense, the AI community observed this frame problem paper, and they said, this is really damning. We basically can't make scientific AI. What are we going to do about it? Well, not a damn thing. We're going to ignore it, and we're going to use toy problems. So they didn't learn their lesson back in the 60s, 70s, 80s, 90s, and now we're basically at the situation where I can say the frame problem is damning all of the model-based AIs as being fallible. It damns every intelligence, no matter how you implement it, as being fallible, because the world changes behind your back and you're going to make a mistake. And this affects things like the danger of AI becoming super intelligent and killing off humanity just for good measure. It's not going to do that. There is no absolute, perfect, omniscient, godlike, infallible, omniscient superintelligence. That's just another reductionist pipe dream. And it doesn't exist. It will never exist. It can't work. We would have to, if you wanted to have something that understood everything scientifically, you'd have to track every water molecule in the ocean. And this is basically people who say, well, let's do that. I call that the computronium approach, where you want to turn the solar system into computronium so you can simulate the ocean. Well, I want AI in my lifetime, so I'm working with solutions that don't require a computronium, okay?
Be nice to have, wouldn't it?
Yeah, no, it would just lead us astray. I mean, we create systems that continuously learn from their own mistakes in the world. Yes, they will make mistakes just like everybody else, but by learning from them rather than having to make a new model from scratch from the outside or whatever, we can build basically a true intelligence, as true as we are.
Interestingly, Ray Kurzweil doesn't believe that general intelligence is a useful term. He thinks that narrow AI, at least last time I checked, will broaden and then intersect with other narrow AIs, and I guess the trunks of these narrow trees will widen until you get like a thick enough forest, such that you'll have a system that will be able to be general. So the working on the generality problem, or the understanding problem, I imagine too, to him is folly. That's his. Well, that may be a bastardization of his view. Sorry, Kurzweil, if I'm misinterpreting you. But yeah, what would you say to that?
Well, Kurzweil was in AI heavily even before 2012, and that colors his view of the world into being largely reductionist. I don't know if he has changed after 2012 or not. He's at Google, so he at least getting influenced by those. But as I understand it, he's not working in the brain group, etc. Who knows? The point is that the terminology even used about these problems, the term general and narrow AI, etc., they were okay back in the olden days. Some sense. Narrow AIs was everything we did, which was a partial solution to the AI problem. And general AI was this thing that nobody knew how to do, that would basically encompass everything. And this is a term coined by Peter Voss and Goertzel mostly, but it was it was okay back then, but right now I would like to say that the split into narrow and AI, AGI, etc., and into narrow versus AGI, it's not productive anymore. It's not going to help us. It's not going to provide implementation hints. We don't know how to make a general AGI. What we do know, what I do know, is basically that there's a difference between machines that understand and machines that reason. And we have to start with the understanding machines. You cannot reason about that which we do not understand. And all of the old AI systems, they basically were stuck behind this misunderstanding that they thought that they could build everything with reasoning. And that's just not true. And so nowadays, I like to say, okay, I don't like to talk about AI at all, one way or the other. My systems are called understanding machines. They are not narrow AI, general AI, anything like that. They just understand. They are not AIs because they don't reason. I claim basically that my systems are not ever going to be dangerous because they can't reason. They can't be full-blown intelligence. All they're good for is understanding text. And that's a very limited task. It's a very limited task that worth $1 trillion because all the industries want to use text understanding for something. Everybody. Absolutely. Yeah. So solve the simpler problem, basically.
Yeah. So where do you see when do you see this being achieved? Having like a good enough natural language understanding, such that it will do everything that you can imagine a company wanting to do with it. That is, right. Sort of understanding the global Wikipedia and then be able to put the pieces together, even where humans haven't.
We are getting very close, and I'm not necessarily the only one working on these things in this manner. Google just advertised another big step forward in the BERT system, which beats most natural language process, NLP, and some so-called glue benchmarks quite handsomely. So people are making progress towards these understanding machines, and I feel like I'm pretty well along with my stuff, and we are actually working on a product that will provide understanding as a service, if you will, in the Amazon cloud or in the Google cloud, where you send in a piece of text and you get back a set of numbers, which you can treat as a Python set, if you will, if you're programming in Python, and you can then do set operations on those numbers, and basically those numbers tell you what a sentence meant. The way you use this is that suppose you wanted to detect harassment in postings on Facebook or elsewhere. What you could do is you could enter a bunch of harassment statements into the system, and you get back sets of numbers for each one of those. And you store those numbers away, and then when you get this posting, you send the posting to my system, and it comes back with another set of numbers, and if there's a significant overlap to the harassment numbers, it's harassment. And it doesn't matter how the people are phrasing it. It's basically what we're striving to in our service is what we call semantic consistency or semantic repeatability. We are getting you the same tokens back no matter how they phrase it. And that would simply, you can directly use, if you're building a chatbot or any kind of system that requires the use of language, you can directly put those tokens into your business logic using Python set theory or other things like that, set operations, and basically sort out whether it's category A or B or whatever you want to do with it.
Right. So the number from 1 to 100 represents its likelihood of being harassment. Is that correct?
Nope. Okay. Sorry. There's going to be I don't know 60 numbers coming back, and 14 of those are common for every harassment case.
Oh, okay.
And it's easy for you to determine which ones those 14 are if you give it 20 different statements. And those are the ones you put aside, and those are the ones you detect in everything that comes back. So you have to do a little bit of work afterwards. I mean, we could do it for you, but we will rather just post sample programs to GitHub about how to do it because it gives you more control in your end. We just provide a service where you feed text in and you get concepts out.
Nice. So this is available for people now to use?
No, we have a few months left to go on this. First of all, we need to get our numbers a little bit higher than we had them, but I mean 4% is not quite good enough. There's a second level of semantics that we need to get to, which we haven't gotten to yet, but we know exactly how to do it. At the moment, the speed of development in my company is basically a matter of money. We don't have quite the resources to go full tilt forward on this, we have to do it with one researcher instead of two, et cetera, et cetera. So it's this could be a few months away if we just had the funding, put it that way.
True. So I don't know how much you can actually talk about this, but what are some fundamental ways that your system of approaching understanding is different from other people's who you feel may be on the right track, or on a close to right track? How would you describe, would you say Peter Voss is on a similar track to you? With his,
no, Peter Voss is definitely not on a similar track. Peter Voss's systems, as far as I have seen them, are reductionist. For instance, they are not general. I asked him if his system could be made to work in a different language, and he said, no, you had to reprogram everything, which indicates that there are language models in there. My systems can learn Japanese, French, Spanish, whatever, because they start from scratch. And so Peter's systems don't. And so therefore I conclude, I don't know if it's entirely correct or not, but I conclude that those systems are mostly reductionist, at least. I can talk about organic learning a little bit. Would you like that?
Yeah, sure. Organic learning.
So organic learning is my name for this thing you see running behind me. It's the fourth name I have for it. It used to be called artificial intuition once upon a time. But the success of deep learning was so big I couldn't resist the temptation to rename it again. Basically, like I said, the deep learning got popular in 2012, and tens of thousands of researchers are working on it now. And what's sad, in my opinion, is that everybody sees that deep learning works. It's the first deep neural network solution that they've ever seen. And nobody's looking for any others. They all think that that's like the only thing that works. Well, there's LSTM, there's a number of variants of deep learning, but they're all in the same family. They all use these arrays of tensors and arrays of floating point numbers that they push through graphics processors. Nobody's looking for anything else in the deep neural network space. Why? There could be much better systems out there. We just happened to stumble upon deep learning as the first one. I mean, happen to stumble is probably unfair to Hinton, but because he spent 34 years working to get to this point, just like I spent 17 years to get to organic learning to working. But still, why doesn't anybody else believe that there's alternatives to deep learning that could work? So organic learning is such an alternative, and I started writing it in 2001, January 1, in fact. And I've been working on it for 17 plus years now. Well, it's 2018, so yeah. But on July 19th of 2017, it actually started working to a quite reasonable degree. I had never gotten under 24% error rate, and here you saw this one started out at 19. Yeah, so we're doing a lot better than we were, and that's because we understand more about these things. I say we because I didn't work on this alone. Over these 17 years, I had 7 other people help me out on and off over the time, and I paid some of them salary, and a lot of them have worked for free, and so on. But it's not just me; it's a teamwork. Although I have written out of the 21 experimental systems, this is gadget number 21, as we call it. 3 of them were written by other people in their entirety, and I wrote all the others. I wrote this one. And so organic learning is basically it's a deep neural network, just like deep learning is, but it's much more natural. It's much more brain-like, if you will. And if you want to write a neural network simulation in a computer, you're more likely to start with neuron and connect them with the synapse, individual neurons and individual synapses. That's like the most obvious model you can think of. And it doesn't work. What do? You try to find more efficiencies. And this is my speculation of what happened with Hinton, is that he basically figured out that if he could use matrix algebra, he could solve a lot more connections faster. So he went that route, and that started working. But in essence, the discrete neuron model where you have discrete neurons, discrete Java objects in my case, or discrete any kind of object in some other language. That is a more natural or brain-like or a more obvious starting point. The reason we don't have them was that just like hint and stuff, just like neural networks in general in the 80s and the 90s didn't work because our machines were too small and our corpora were too small. The same was true for these discrete models. And so I basically picked up the shards of neural networks that we had from the 80s and 90s of the discrete kind. And I started working on those in 2001. And by 2016, the machines have caught up in size. And now it was a viable solution, just like hint and stuff got viable in 2006. So it's just a parallel. It's just a fruit of a different tree. Now let's talk about the details here. So what I have is, instead of arrays of floating point numbers, I have individual neurons. And I start out with an empty machine. And when I read a letter like T, I create a neuron. If it's the first time I see the T, I create a neuron for the T, which is now the T input neuron. And it will then try to signal to other neurons, and there aren't any there, so it makes a new one. And tries and so on. And basically for every letter you read, if you have an input neuron, you reuse it, and you reuse your path of signaling. And if you don't have an input neuron, you make a new one. And so in general, that's a strategy. If you have a neuron in the right place, you use it. Otherwise, you make one and put it there. So we call it a connectome algorithm, an algorithm that basically makes decisions about when to make new neurons and where to connect the synapses. And it starts out empty, and then it grows in something we can compare to organic growth in the jungle, and that's why it's called organic learning.
You mean organic growth in the brain, or organic growth in the jungle, like trees and? Yes,
organic growth in the jungle like trees. Our system basically grows without any central control, without any rules. It has basically, it's all emergent. The structure that we get from reading 100 books is basically an emergent effect of what's in the books.
Mm-hmm. Now, emergence is a bit of a dirty word amongst some crowds. Where do you think they're going wrong with it? I mean, like, what is it? Why do people dislike the idea of emergence and supervenience?
Because it's contrary to reductionism. It can't be. Basically, emergence is if you have a system of emergent effects and you break it down into pieces, the effect goes away. Take an emergent effect such as I don't know, quality or radio reception. I mean, you have a radio, you take it apart into pieces and you try to explain where the singing was coming from. It's not there in the pieces. Quality or lifespan are things that are emergent effects of all the components in the car or all the components in the human body, etc. And it can't be determined by taking things apart and making models. And so I have a video called Bizarre Systems, where I basically discuss this problem that emergence is one of 10 factors that make science impossible. Not having in data is the most biggest one for all the AI problems. You don't never have complete input data. Mm-hmm. But emergence is definitely a problem.
Yeah. So how does your system differ from hybrid deep learning systems? Is there something around the traditional deep learning model, even though hybridized needs to sort of change?
Well, it's not hybrid in any real sense. I mean, deep learning is a holistic system, just like my system is. It solves the problem in the problem domain. It doesn't use external models. It builds internal models. I actually make a difference between models which I claim are context-free and patterns which I claim are mixed with context or content. In the beginning, at the bottom, you have content coming in like pixels or characters. And then you form concepts in the middle that are expressed as patterns, and they have some residual attachment to the input, such as it was in this specific case. But then you go abstract more and more and more, and when you abstract it enough, you have a context-free version of whatever you have. Like you have the prototypical chair, or you have the prototypical car, or whatever. That's your highest level context-free model of a car, and it's different from my car or my chair, which is what we started with, because those had residual context of being in my house and my garage. So to me, models are basically just the topmost things. But people say that models are all over the brain, so fine. So what these systems do is they're basically building their own models at some level. In my system, I say they're building multiple overlapping recursive patterns. And those patterns eventually thin out to become just the highest level concepts that exist, and those can be close enough to models if we look at them, if they don't have any residual context.
Okay, is this similar to what you mean by partial reductions?
Yes.
In your writing?
Yeah, you go halfway. I mean, you play tennis with partial reductions because you don't have to go to a model of a tennis ball to hit it. You can just go hit this ball.
Like if you're playing billiards, you might be really like intuitive at doing it, but at some points in the game, you might be partially reductionistic, right?
So there are some people who play entirely they sit down and they hit the thing, and it's always, I mean, you should watch Ronnie O'Sullivan play snooker sometime. I mean, yeah. So some people, they basically have played enough that all of the stuff that they need to play billiards well is in their mind. It's all short circuits at low levels that do exactly the right thing. And some people, they wish they had a ruler and a degree thing on the table so they could measure the reflecting angle. And they are playing it reductionistically to some extent. But it's basically, pool is a simple enough problem that you can solve it both ways. There's others like that. Like if you want to shoot a cannon, you can shoot the cannon. Modern computers on cannons will basically shoot down an airplane out of the sky by computing everything completely reductionistically. But if you're in a war and you're shooting with a gun, or just shooting at the range or whatever, you don't have computers to help you aim the thing. You're shooting holistically. You have to basically practice until you shoot better. That's the only way. You don't measure angles at the shooting range.
I'm not sure if I'm correct, but one of the first uses of the terms of computers were people who would calculate trajectories of cannon.
Exactly. Yes. They had a desire to increase the hit rate. And the way they thought that they were going to do that was by computation, and it works. But you can't. You don't have that on a handgun. I mean, you have a sight at best, but But shooting from the hip or whatever, that's definitely holistic.
So where to from here in terms of like holistic development or understanding machines? What are some of the most are all the problems that need to be solved? Have they all been worked on, do you think, or is there some things that we don't quite know what to solve? Is there still unknown unknowns, or is there still known unknowns that aren't being
right? I can, in my opinion, I mean, I'm looking at what I am doing. I think that I have a handle on understanding. The next phase for my company is language. It's language generation, that you basically can take like I said, your deep generation from brain state to a sentence that comes out. That would be very useful even for debugging, but that's what everybody's waiting for. If we had that, we could make question answering systems and stuff like that. And the third phase is called contiguous rolling topic mixed initiative dialogue, where the sound computer asks clarifying questions and sometimes takes the initiative in a conversation. And that's much like the movie Her, or that's like Siri 5.0, which doesn't exist yet, but which I would love to be able to build. And so those are like incremental steps, if you will, towards something we can talk to, which we can perceive as intelligent. No Turing test necessary. I mean, we know this is Siri 5.0. We still know it's intelligent. It's going to be obvious in the first 3 sentences. So that's and I think that these incremental steps are small enough that a company less than 50 people could do it in 5 years, all the way to the top. I mean, we are months away or less from publishing an understanding machine.
Interesting. So do you think you'd be able to translate what you're doing with natural language understanding into like code understanding, like, or being able to program? And
yes, these are all things we wish we could do, and we don't know yet how good they will be at this. And we don't know how much of a computer you need for this. I mean, I'm estimating that you can get I'm estimating you can get most of English, enough of English to be useful in most situations in a machine with about 1 terabyte of memory, RAM. Maybe. And Intel is basically making chips that are getting up there. So we might see understanding machines in your cell phones within the next, I don't know, 4 or 5 years. Who knows? Depends on how popular it gets, how quickly this develops, and so on. By the way, I can see on my screen here that we have we've gone down to 99% error at the moment. So yeah, we don't have to look at it yet.
Right. Yeah. Mm-hmm. Well, I guess, what else? Like, I'm just wondering, like, in what ways do you think the salient aspects in which you disagree with some of your, with some of the peers that you most respect?
Well, all of the people who basically built models of something, built models of the world, built models of language, built models of blocks worlds or whatever, they were good results in their day, but they are not really on the path to anything we can call AI. And I basically disagree with everything. I mean, nowadays, remember, I was doing AI before that. I've been doing expert systems and other useful things myself, but they were not really understanding machines. They didn't understand anything. They were handmade programs that I made that then just did what they did, and it looked impressive, so we called it AI. But yeah, I basically say that, yes, AI has many interesting techniques, and some of them are still quite useful. Like pathfinding in your car, for instance, is done using an algorithm that was regarded as AI 10 years ago. But the big difference is basically between me and everybody who insists that intelligence has to be logical in some sense, and that's the biggest. I mean, I say intelligence has to be pre-scientific or unscientific. That's the only, because we never, for instance, you have to jump to conclusions of scant evidence, because scant evidence is all you'll ever have in the real world. I mean, AIs have to live in our world. They can't live in the pure mathematical space. That would be silly. They have to live in our world. They have to deal with the fact that the world changes behind your back. They have to deal with uncertainty. They have to deal with conflicting inputs, etc., and in a graceful manner. And that's basically, that throws science out the window. You have to do pre-scientific stuff. And it's called pre-scientific for 2 reasons. One is that people in the world were not scientific before 1650. We only invented science in 1650, but they were still intelligent. Okay, think about that. And the second thing is that you have to do the unscientific understanding before you can apply the scientific reasoning on top. So don't reason about something you don't understand, but the understanding is still holistic, still basically best effort based on available evidence. And we're happy we will be shown to be wrong many times. There's no way around that.
So, have you what do you think of Stephen Wolfram's new kind of science? Have you read that?
Wolfram is heavy.
Is there some similarities?
No, none whatsoever, I don't think. I like the ideas. I'm impressed by his cellular automata and stuff, and he's a very, very good programmer and a very good reductionist, and we should let him do what he's doing. I don't think it's going to have any impact on long-term understanding machines. And that's true for most of the people who have done good jobs as reductionists. They should stay where they are and keep doing it. I hope to see a generation of basically I don't know, students all over the place graduate with ideas that science isn't the end all of everything, and that we can actually get somewhere with unscientific methods, pre-scientific methods, such as neural networks.
Interesting that you don't classify that as science. A lot of people would, and I'm just wondering there if you're frightening away people by saying it's not scientific.
I realize that it's controversial, and I kind of like the idea of being controversial in this manner, but it's the absolute truth. If you insist on doing everything scientific, you are going to lose it. Science, for instance, I have on my artificial intuition page, the old one, I have a whole chapter called The Trade-Off. And the trade-off is basically that if you want to be scientific, then you have optimality. You can find all the answers. You can find the best answer. You have completeness. You can find all the answers. You have repeatability. You get the same answer every time. You have parsimony. You're not wasting your resources. You have transparency of process, which means you understand how the answer was arrived at. And you have a scrutability of the answer, which means you understand the answer after you have it. This is true for basically for science, and everybody loves these features. You can find the best solution, you can find all of them. When you are switching away from scientific methods, for instance, if you're switching to something as simple as a genetic algorithm, you've thrown all 6 of them away. You can't use them. You have none of those features anymore. You have gone holistic. Genetic algorithms, genetic programming, deep learning, and organic learning, they're all basically part of a new wave of solving problems that are a holistic way of solving problems in the problem domain. And now those 6 guarantees are gone. And instead you have very interesting features such as the ability to do reduction, the ability and abstraction, the ability to self-repair if, let me take them in order. I can't remember them. Reduction, abstraction, salience, prediction, self-repair, all kinds of cool stuff. You can read my blog about that you don't have in the scientific realm. If you do things scientifically, you can't do reduction, because reduction is assumed to be done before you go scientific. By a human.
Yeah. So it's like, okay, so we've covered a lot of ground here. If there's anything that we haven't covered that you think is worth bringing up.
We can take one last look at my experiment. How's that?
Sure, sounds good.
So what we can see here is after running for 3,000 seconds, it has read 3 megabytes of text. It spent 2,383 seconds learning at the kilobyte plus per second, and it reached 6% error rate in that time. If it went for another megabyte or 2, it would basically hit the 4% mark, which is highlighted in blue here. This is 0, this is 4%, and 100% is 2 feet to the right. But that's what we've gone from 19% to 6% in basically reading something like 4 books.
Interesting. It got on line 3. It seemed to have got slightly worse.
Oh yes. It found some. It discovered that it had jumped to conclusions and found better conclusions to jump to.
Oh, okay, so it's self-prepared.
It's a little bit of catastrophic forgetting. Basically, we see these all the time. I mean, if I had a straight line going here, I probably had faked the data. But yeah, this is what happens every time you train. You have some kind of up and down. And at the moment, one of the troubles we're having with the system, one of the problems we're having with the system right now is that it will bounce. It will go down to 2-3% and stay there for a while, and then we start overlearning and it goes back out again, and we end up with 5-6%. And so we want to basically have completely certain ways of preventing the overlearning from happening. We're working on that.
Fair enough there. Okay, well, yeah, so if there's any, so it's been wonderful, and I've learned a lot. Actually, I've done a lot of reading before this, so like it does make sense to me. If there's any concluding remarks, or if you want to if there's a sort of, compressed version of something you'd like people to take away, if not, if they were watching until the end here, then
well, I guess that my main remark would be that these things are happening. Some things are happening faster than you think, and the things that you're going to see happening soon are going to be very different from what you expected. If you're especially if what you expect is based on pre-2012 ideas about AI. Because those are obsolete. Those are obsolete. You have to basically start at 2012 and see what we can do with the methods that we discovered after that. Because those are going to be the fundamental foundation that we're building all our AI and understanding machine work on hence after.
Well, a lot of people are considering that they'll see smarter than human intelligence or some kind of singularity, and it's not something you completely agree with. I mean, maybe smarter than human, but like not a boom.
There are hard limits on intelligence. The frame problem puts a hard limit on intelligence because at some point every intelligence will make mistakes because of the frame problem, because the world changed and they had a bad model. So absolute intelligence is impossible. Absolutely perfect intelligence is impossible. And so I'm estimating that, yes, we will have very competent machines. They will know a lot of stuff. They will be able to operate very quickly. They will be able to do complementary searches for what they don't know very quickly. All of these are good things, but they are not really better at problem solving than we are. And they may not, so there's all kinds of little limits on in what way they can be better. And yes, they will be better than humans, but not radically so, and definitely not infinitely so. So from those points of view, with that background, I mean, for instance, consider this, that for the next decade or so, the most common understanding machine, at least, will live in the cloud. It will be a machine that we give a document like a web page and say, evaluate this for quality. And it comes back and says the quality is such and such. And then we kill it because it's done its job and we don't want it to learn anything from it. So the average lifespan for an AI in the next decade is going to be 50 milliseconds or something. And those are going to be read-only intelligences. We make an intelligence, we teach it everything we want it to know at the factory, so to speak. And then we sell it to whoever, Google, Amazon, whatever, wants to put it in the cloud for any purpose. And they make 1 million of those and they pay us licenses for whatever. But those are going to be basically frozen machines. They don't learn anything else. They basically understand text and they're doing that job and nothing else, and they are not dangerous, and they're not gonna get to be dangerous.
They're sort of narrow in a sense, right?
No, they're not narrow. They are fully general machines. We just froze them. They're frozen general intelligences.
And you don't let them just go on thinking. Somebody will do that. So surely someone will try and experiment and see what happens.
Oh yeah, we're going to do it ourselves too. I mean, we want to move forward on this thing, but like I said, for the next decade or so, we're going to see a lot of intelligences that are very ephemeral, very short-lived. They do a single task and they do it well. They are not AGIs; they are understanding machines, but that's still worth a lot of money.
What about the decade after that?
I wouldn't even dare to predict what's going to happen 5 years from now.
Fair enough. Well, it's been wonderful speaking to you, Monica.
This was fun. Thank you very much. Good questions.
What you're doing, and it's great. So keep up the great work. And look, I'm looking forward to seeing what the world will look like when we have more understanding in our machines. I think it is a rather overlooked problem, and people chasing things like generality and just some of the common problems in AI, but aren't necessarily focusing on the understanding aspect.
Yeah, generality is a solved problem, in my opinion. Read my blog.
Okay, sure. Yeah. Well, I'll put some links to this underneath the video here. So thanks for everybody for tuning in and listening. And it's been wonderful. And please remember to subscribe because there'll be more of these types of videos in the future.
Thank you. Bye.
Thank you.